So please welcome on stage Michael, aka Greycast, who will introduce us with an exciting project called Kaitai Struct, so dissecting media file formats.
Hello everyone, and thank you for joining me today. My name is Michael Yakshin, and I'd like to talk about dissecting media file formats today with the tool named Kaitai Struct. So what's the idea? Media file formats grow complex and more complex every day. Media software developers have to deal with a multitude of different media file formats. Some of them are well documented, but still pretty complex to process. Some of them are proprietary and undocumented and need to be reverse engineered. It's even more complicated task and requires quite a few hurdles to jump. For example, one need to do the proper black box reverse engineering to be included into free and open source project without major legal problems. One need to do lots of testing, making some hypotheses, proving them right or wrong, and doing some decisions, mapping some proprietary format step by step, exploring it, and doing some kind of description or specification of such problem. Basically, the mission that such a developer must undertake is going from byte representation of file format in a stream, loading into memory, and sometimes going back from memory to a stream. That is, we have some kind of stream that needs to be dissected into some objects laid out in memory, usually in some kind of tree or graph of objects. Typical development workflow for such a process involves writing some parsing code with certain programming language. Then you write some extra debugging code to ensure that it actually works, because you need to somehow prove that it works. You either dump it to the screen, check some assertions, run with it with a debugger or something like that. Then you just basically debug it till you drop, because parsing binary formats is, well, not exactly a trivial task. There are quite a few pitfalls to overcome, like going over some boundary inside some structure, dealing with endiness, dealing with byte alignment, dealing with a few other things like assertions, checks, barely specified formats, some special cases, conditional reading, writing, etc., etc. As soon as you finish such a big task, you get some sort of parsing library that loads objects from stream into memory. But what then? If you want to support some other programming language, you just basically need to redo the whole process from the start, doing basically the same code in some other programming language imperatively. Actually, almost every media format library I've encountered has these dumping tools. On this slide, I've listed some of them. Then they're not just for random reason. They're for reason. They are needed by developers of these two libraries to debug their tools and to see if they really work. Needless to say that errors in file format libraries can be really devastatingly dangerous. Almost every such an error, such as buffer overflow, such as reading beyond some part of structure, interpreting something wrongly because of human errors in writing the code, etc., etc., are almost always remotely exploitable. They frequently provide arbitrary code execution, especially if we're talking about buffer overflows in libraries written in languages such as C. They leak information. They usually can lead to denial of service errors. For example, in libpng since 2010, there were 22 vulnerabilities, and quite a few of them are really dangerous. In libdebug, for example, there are 4 vulnerabilities, but they're still dangerous as well. If we'll revert to the start and see what file format specifications exist, we'll discover that there is no single universally accepted standard. Actually, if we'll take a look at the documents provided by file format authors, there are quite a few things invented to describe a file format, such as, for example, C structures, as we see here with ELF headers, such as intricate tables, as we see here with network tables protocols, such as even more intricate tables, as we see here with some random page describing Microsoft Word document format that maps some bytes, bits, and try to explain its values. Network protocol engineers have something better to rescue. They've got Wireshark that is universally accepted to be a tool of trade that allows to dissect the packets and see what's inside in some kind of tree format. Basically, you have the dump. You can point at any byte in the dump and see what values in protocol in the packets it corresponds to, and vice versa. But what about the same stuff for media files? It's a bit complicated. There are quite a few proprietary tools available, such as 101 editor or Hexinate or Synalizeit, as some of you may be familiar with. But generally, there is no universally accepted, or at least a tool that supports enough popular formats to dissect and to build upon. Well, so basically we've tried to fulfill this whole and go actually one step ahead of it. So I'd like to present a Kaitai Struct project, which is declarative file format specification language. All the words in this phrase are actually meaningful. The emphasis is on the declarative. It means that we do not actually specify how to read the format, but we specify what is inside the format. And it's harder to implement in some cases, but it gives us quite a few advantages I'd like to show a bit further in the presentation. We can compile our case Y file that we've set up with the file format specification into ready-made parsers libraries in quite a few target programming languages that I'll demonstrate further. And quite as well, we can visualize, dump, and debug all these file format specifications using several tools that were built around the Kaitai Struct project, such as visualization tools, such as WebID, that I'll demonstrate further as well. KSY format is YAML-based, and that's actually a good thing because it's very easy to write your own tools. For example, it's quite a snap to write a tool that would embed one KSY file into another KSY file. It's generally a matter of writing a script in 5 or 10 lines, and it's quite easy. It's, last but not least, it's free and liber. We use GPLv3 for the compiler, and actually generated code uses some runtime libraries that we supply as well. and they are MIT or Apache 2 licensed. So even if the compiler is GPL, it's possible to use the proceedings of the compiler in proprietary projects as well. We support 8 target languages right now. It's C++, C#, Java, JavaScript, Perl, PHP, Python, and Ruby. As a bonus, we support output to graphics. I'll demonstrate it further. It's quite interesting side project as well. As experimental features, right now we are developing Swift support. We're developing support for exporting case-y files as Wireshark dissectors to be able to load the same declared formats into the Wireshark interface and see there, and quite a few other probably interesting target formats. So how does it look? The natural API generated by Kaitai Struct looks something like that. Here we have a demonstration of GIF file, GIF file, loaded. Generally, the Kaitai Struct file declares a tree of objects. Here, for example, we have the header, the logical screen descriptor, global color table, etc., etc. And generally, it boils down to traversing this tree of objects from some start that, for example, in this code in Java starts with gif.from file that loads that parses some GIF data from the file, and then you just do this file .something and extract the data right away. For example, this is one liner that shows the screen width and height, which is actually the dimensions with visible fragment of GIF image right away in one line of code. This is our web IDE. Probably it's much better to just demonstrate it right away. This is probably now the main working place of a developer that wants to get his or her hands dirty with Kaitai Struct. Here we have simultaneously an editor to see and edit the case-y file. It's on upper left corner. In upper right corner there is a hex dump of some loaded file. Here we have a Microsoft AVI file and its corresponding format description. As you may have seen in such editors like 101 editor or Hexinator or other proprietary editors, it's possible to select any byte in the stream and go exactly to some value in the object tree in lower bottom corner to see what this byte corresponds to. And as well, one can traverse open and close arbitrary objects in the object tree as well and see how it looks like. It's fully interactive. Changing a single symbol in the case-y code recompiles everything conservatively and tries to re-implement, reiterate, reparse the file in a new way that you just specified. So for example, if you add some lines of code that add a parsing of some new field, it would just appear right away. You don't need to basically just doing anything. For those who want some more console hardcore style parsing, there is also a console visualizer. Here we have the JPEG file loaded into it. It doesn't look just as flashy as the web one, but it works just as well. It doesn't feature a separate editor, of course. You're expected to have your own editor in console or whatever you want to use in some other window. So it focuses just on visualization. You have the same tree, you have the same binary dump. You can traverse it and see if the file specification you just entered matches what you expect to see or not. This is how our case Y files look like. Basically, it's YAML. It allows us to set up some fields, some field types, and that is important because it's declarative and not imperative. On the left, we see our declarative specification. On the right, we see what it compiles usually to into some kind of imperative code. Note that we do not have things like while loops. We do not have things like direct ifs, any conditional controls, any jumps, basically any code flow that is imminent in imperative implementations. We just describe the file structures. If there is some repetitions, we enter it as repetitions. If there is some conditional parsing, we enter it as conditional parsing. And it brings up quite a few possibilities, interesting possibilities that are possible. We have quite a few built-in data types, such as integers, floats, unaligned bit integers and bit fields, strings, row byte arrays, enums. And of course, we allow to define user-defined data types. We have sequential parsing fields one by one in sequence. We have out-of-order parsing, something called instances. So you can seek in a file actually to do some parsing of other parts of file by some index or offset. We have calculated attributes to ease representation of something that we've got from the file in some more popular form. We got checking for magic signatures, such as fixing content, counter, for example, in headers. We have conditional parsing. We have type switching on a condition, something like switch. We have repetitions until the end of stream, repetitions in predefined number of iterations, or until some condition is met. We have powerful expression language that could be used almost everywhere, and that's a good thing because it actually compiles into direct expression code in some other languages. For example, this one shows how we can parse the attribute named full-len that allows us to specify unsigned integer 4 bytes long in the first place, and then we parse as many elements as we need, calculating the number of elements as full-len minus 4 divided by 6. So it is how it compiles to C++. This is how it compiles to Python. You can see that the code is quite different. And it's how it compiles to JavaScript. Another difference is that, for example, JavaScript doesn't have the integer division, so we implement it with math.flow. And that's another one that I wanted to demonstrate interesting stuff about the graphless visualization. Basically, we compile stuff to graphless, and this is what we've got. It's a human-readable diagram that one can pass to his colleagues, one can pass to other people to just take a look at the format and implement it, for example, in some other programs. We've got a ground repository of formats, including tons of formats right now. It's quite interesting. You can find it at our GitHub page and see for yourself if there will be anything interesting for you there. There are quite a few image file formats, video file formats, audio file formats, archives, documents, executables, file systems, etc., etc. Thanks for your attention. I'd like to see if any questions arises.
There was one example where there was a length field and you had the length -4 divided by 6. So in one of the examples, by the way, showed how to compile the different code. I was wondering what happens if the length is 3. So I would get negative thing in the division. So would it catch that and tell me this input is strange? Or
yeah, the question was about handling incorrect values in complex expression language expressions. So basically there is no internal checking in Kaitai Struct. It just compiles the expression as I showed you, and in runtime it will probably arise some sort of exception or error, and this would be specific to a particular target language that you compile this code to. Please?
Yeah, so I noticed you have mostly container formats in that list, which are generally roughly byte stream based. What about codecs that have big stream fields that are quite complicated, like most of Hoffman codes or Golang codes or various different, they have much more complex bit streams that we'd like to analyze. Is it possible to write in your definitive language the way that you parse these bit streams?
Yes, since, yeah, sorry. The question was about parsing bit streams with more complex codecs like Hoffman codes, etc., etc. So yeah, since version 1.0.6, we have support for reading bit streams. It's slowly growing. Probably it's not very optimal to parse bit streams per se to fulfill simple operations like unpacking something or uncompressing something. Probably it's more efficient to use some special processing onto the whole byte stream here, but it also can be done. I don't see any major problems here.
Your compilers that are generating the code, can they also generate streaming parsers, or is it always something that needs the whole file before it can do anything?
Could you repeat it a bit louder?
Your compilers that are generating the parser code, can they generate streaming parsers or only parsers that need the whole file? Like in the case of
streaming parsers of strings.
If reading a stream instead of a whole, you have to read a whole file, or can you only read, partially read a stream when you
Right now, the API, repeating the question, yeah? The question was about reading something from a stream, not from the whole file from the disk. Right now, the API allows to basically do reading and parsing from two sources, from a file on disk or from arbitrary array in memory. If you can organize the parser in some way that would be, for example, chunk-based, that would parse one chunk and then stop, it's no problem to go with this chunk-based stream that you would somehow buffer in memory and add to this buffer again and again and recall the parser. So I guess that would be it.
We still have time for one last question, so please make it well. So who is still motivated for that? Okay, you were the first.
Okay.
Can you add annotation in YAML file to display more human readable things?
There are several the question was about adding annotations to YAML file to have more human readable representation of whatever's going on there. There are quite a few possibilities to do so. We are allowed to add some annotations to fields to be parsed as doc strings into the target code. So, for example, if you load it into IDE, you just see whatever the command for the field are. We allow in Web IDE there are several syntaxes that allows you to mark up some formatting for the representation. For example, choosing the hex representation, binary representation, or decimal representation, etc., etc. And last but not least, you can do calculated values that allow you to represent something in more human readable way as well. Thanks.
For example, a bit flag. How do you
The bit flags are parsed using the bit parsing syntax usually, and you usually get them as separate fields that you can basically touch in every way you want to.
Okay, well, thank you. I'm sorry, there are a lot of questions, but I'm sure you are available after the